The San Andreas Fault is a continental transform fault that extends roughly 800 miles through California. It forms the tectonic boundary between the Pacific Plate and the North American Plate, and its motion is right-lateral strike-slip. The fault divides into three segments, each with different characteristics and a different degree of earthquake risk, the most significant being the southern segment, which passes within about 35 miles of Los Angeles. The fault was first identified in 1895 by Professor Andrew Lawson of UC Berkeley, who discovered the northern zone. It is often described as having been named after San Andreas Lake, a small body of water that was formed in a valley between the two plates. However, according to some of his reports from 1895 and 1908, Lawson actually named it after the surrounding San Andreas Valley. Following the 1906 San Francisco earthquake, Lawson concluded that the fault extended all the way into Southern California. In 1953, geologist Thomas Dibley astounded the scientific establishment with his conclusion that hundreds of miles of lateral movement could occur along the fault. A project called the San Andreas Fault Observatory at depth near Parkfield, Monterey County, is drilling into the fault to improve prediction and recording of future earthquakes. Fault zones. The northern segment of the fault runs from Hollister, through the Santa Cruz Mountains, epicenter of the 1989 Loma Prieta earthquake, then up the San Francisco Peninsula, where it was first identified by Professor Lawson in 1895, then to offshore at Daly City near Mussel Rock. This is the approximate location of the epicenter of the 1906 San Francisco earthquake. The fault returns onshore at Bolinas Lagoon just north of Stinson Beach in Marin County. It returns underwater through the linear trough of Tomales Bay, which separates the Point Reyes Peninsula from the mainland, runs just east of the Bodega, heads through Bodega Bay and back underwater, returning onshore at Fort Ross. From Fort Ross, the northern segment continues overland, forming in part a linear valley through which the Galala River flows. It goes back offshore at Point Arena. After that, it runs underwater along the coast until it nears Cape Mendocino, where it begins to bend to the west, terminating at the Mendocino Triple Junction. The central segment of the San Andreas Fault runs in a northwestern direction from Parkfield to Hollister, while the southern section of the fault and the parts through Parkfield experience earthquakes. The rest of the central section of the fault exhibits a phenomenon called aseismic creep, where the fault slips continuously without causing earthquakes. The southern segment begins near Bombay Beach, California. Box Canyon, near the Salton Sea, contains upturned strata associated with that section of the fault. The fault then runs along the southern base of the San Bernardino Mountains, crosses through the Cajon Pass and continues northwest along the northern base of the San Gabriel Mountains. These mountains are a result of movement along the San Andreas Fault and are commonly called the Transverse Range. In Palmdale, a portion of the fault is easily examined at a road cut for the Antelope Valley Freeway. The fault continues northwest alongside the Elizabeth Lake Road to the town of Elizabeth Lake. As it passes the towns of Gorman, Tejon Pass and Frazier Park, the fault begins to bend northward, forming the Big Bend. This restraining bend is thought to be where the fault locks up in Southern California, with an earthquake recurrence interval of roughly 140 to 160 years. Northwest of Frazier Park, the fault runs through through the Carrizo Plain, a long, treeless plain where much of the fault is plainly visible. The Elkhorn Scarp defines the fault trace along much of its length within the plain. The southern segment, which stretches from Parkfield in Monterey County all the way to the Salton Sea, is capable of an 8.1-magnitude earthquake. At its closest, this fault passes about 35 miles to the northeast of Los Angeles. Such a large earthquake on this southern segment would kill thousands of people in Los Angeles, San Bernardino, Riverside, and surrounding areas, and cause hundreds of billions of dollars in damage. Plate boundaries. The Pacific Plate, to the west of the fault, is moving in a northwest direction, while the North American Plate to the east is moving toward the southwest, but relatively southeast under the influence of plate tectonics. The rate of slippage averages about 33 to 37 millimeters a year across California. The southwestward motion of the North American Plate towards the Pacific is creating compressional forces along the eastern side of the fault. The effect is expressed as the coast ranges. The northwest movement of the Pacific Plate is also creating significant compressional forces which are especially pronounced where the North American Plate has forced the San Andreas to jog westward. This has led to the formation of the transverse ranges in Southern California and, to a lesser but still significant extent, the Santa Cruz Mountains. Studies of the relative motions of the Pacific and North American plates have shown that only about 75% of the motion can be accounted for in the movements of the San Andreas and its various branch faults. The rest of the motion has been found in an area east of the Sierra Nevada mountains called the Walker Lane or Eastern California Shear Zone. The reason for this is not clear. Several hypotheses have been offered and research is ongoing. One hypothesis, which gained interest following the Landers earthquake in 1992, suggests the plate boundary may be shifting eastward away from the San Andreas towards Walker Lane. Assuming the plate boundary does not change as hypothesized, projected motion indicates that the land mass west of the San Andreas Fault, including Los Angeles, will eventually slide past San Francisco, then continue northwestward toward the Aleutian Trench, over a period of perhaps 20 million years. Formation. The San Andreas began to form in the mid-Cenozoic about 30 mi. At this time, a spreading center between the Pacific Plate and the Farallon Plate was beginning to reach the subduction zone off the western coast of North America. As the relative motion between the Pacific and North American plates was different from the relative motion between the Farallon and North American plates, the spreading ridge began to be subducted, creating a new relative motion and a new style of deformation along the plate boundaries. These geological features are what are chiefly seen along San Andreas Fault. It also includes a possible driver for the deformation of the basin and range, separation of Baja California, and rotation of the transverse range. The main southern section of the San Andreas Fault proper has only existed for about 5 million years. The first known incarnation of the southern part of the fault was Clemens Well-Fenner-San Francisco Fault Zone around 22 to 13 Ma. This system added the San Gabriel Fault as a primary focus of movement between 10 to 5 Ma. Currently, it is believed that the modern San Andreas will eventually transfer its motion toward a fault within the Eastern California Shear Zone. This complicated evolution, especially along the southern segment, is mostly caused by either the Big Bend and/or a difference in the motion vector between the plates and the trend of the fault and its surrounding branches. Study. Early years. The fault was first identified in Northern California California by UC Berkeley geology professor Andrew Lawson in 1895 and named by him after the Laguna San Andreas, a small lake which lies in a linear valley formed by the fault just south of San Francisco. 11 years later, Lawson discovered that the San Andreas Fault stretched southward into Southern California after reviewing the effects of the 1906 San Francisco earthquake. Large-scale lateral movement along the fault was first proposed in a 1953 paper by geologists Mason Hill and Thomas Dibberley. This idea, which was considered radical at the time, has since been vindicated by modern plate tectonics. Current research. Seismologists discovered that the San Andreas Fault near Parkfield in central California consistently produces a magnitude 6.0 earthquake, approximately once every 22 years, following recorded seismic events in 1857, 1881, 1901, 1922, 1934, and 1966. Scientists predicted that another earthquake should occur in Parkfield in 1993. It eventually occurred in 2004. Due to the frequency of predictable activity, Parkfield has become one of the most important areas in the world for large earthquake research. In 2004, work began just north of Parkfield on the San Andreas Fault Observatory at depth. The goal of SAFOD is to drill a hole nearly 3 kilometers into the Earth's crust into the San Andreas Fault. An array of sensors will be installed to record earthquakes that happen near this area. The San Andreas Fault system has been the subject of a flood of studies. In particular, scientific research performed during the last 23 years has given rise to about 3,400 publications. The next big one, a study published in 2006 in the journal Nature, found that the San Andreas Fault has reached a sufficient stress level for an earthquake of magnitude greater than 7.0 on the moment magnitude scale to occur. This study also found that the risk of a large earthquake may be increasing more rapidly than scientists had previously believed. Moreover, the risk is now concentrated on the southern section of the fault, i.e., the region around Los Angeles, because massive earthquakes have occurred relatively recently on the central and northern segments of the fault, while the southern section has not seen any similar rupture for at least 300 years. According to this study, a massive earthquake on that southern section of the San Andreas Fault would result in major damage to the Palm Springs, Indio metropolitan area and other cities in San Bernardino, Riverside and Imperial counties in California, a Mexicali municipality in Baja California. It would be strongly felt throughout much of Southern California, including densely populated areas of Los Angeles County, Ventura County, Orange County, San Diego County, Ensenada Municipality and Tijuana Municipality, Baja California, San Luis Rio Colorado, Sonora and Yuma, Arizona. Older buildings would be especially prone to damage or collapse, as wood buildings built on unconsolidated gravel or in coastal areas where water tables are high. The paper concluded, the information available suggests that the fault is ready for the next big earthquake, but exactly when the triggering will happen and when the earthquake will occur we cannot tell. It could be tomorrow or it could be 10 years or more from now. Nevertheless, in the 10 years since the publication there has not been a substantial quake in the Los Angeles area, and 2 major reports issued by the U.S. Geological Survey have made variable predictions as to the risk of future seismic events. The ability to predict major earthquakes with sufficient precision to warrant increased precautions has remained elusive. The U.S. Geological Survey most recent forecast, known as UCERF3, released in November 2013, estimated that an earthquake of magnitude 6.7 or greater occurs about once every 6.7 years statewide. The same report also estimated there is a 7% probability that an earthquake of magnitude 8.0 or greater will occur in the next 30 years somewhere along the San Andreas Fault. A different USGS study in 2008 tried to assess the physical, social and economic consequences of a major earthquake in Southern California. The study predicted that a magnitude 7.8 earthquake along the southern San Andreas Fault could cause about 1,800 deaths and $213 billion in damage. Cascadia connection. Recent studies of past earthquakes indicate that there is a correlation in time between seismic events on the northern San Andreas Fault and the southern part of the Cascadia subduction zone. Scientists believe quakes on the Cascadia subduction zone may have triggered most of the major quakes on the northern San Andreas within the past 3,000 years. The evidence also shows the rupture direction going from north to south in each of these time-correlated events. However, the 1906 San Francisco earthquake seems to have been the exception to this correlation because the plate movement was moved mostly from south to north and it was not preceded by a major quake in the Cascadia zone. Earthquakes. The San Andreas Fault has had some notable earthquakes in historic times. 1857 Fort Tejon earthquake. About 350 kilometers were ruptured in central and southern California. Though it is known as the Fort Tejon earthquake, the epicenter is thought to have been located far to the north, just south of Parkfield. 2 deaths were reported. The magnitude was about 7.9. 1906 San Francisco earthquake. About 430 kilometers were ruptured in Northern California. The epicenter was near San Francisco. At least 3,000 people died in the earthquake and subsequent fires. The magnitude was estimated to be 7.8. 1957 San Francisco earthquake, a magnitude 5.7 quake with an epicenter on the San Andreas Fault in the ocean west of San Francisco and Daly City. 1989 Loma Prieta earthquake. About 40 kilometers were ruptured near Santa Cruz, California, causing 63 deaths and moderate damage in certain vulnerable locations in the San Francisco Bay Area. Moment magnitude was about 6.9. The earthquake also postponed Game 3 of the 1989 World Series at Candlestick Park. This quake occurred on the 17th of October 1989, 1704 PDT. 2004 Parkfield earthquake on September 28, 2004, at 10:15 a.m. PDT, a magnitude 6.0 earthquake struck the Parkfield area. It was felt across the state, including the San Francisco Bay Area.